I'd like to welcome everyone to today's webinar, which is based on the August issue of MRS Bulletin, with the topic being 3D bioprinting of organs. I obviously don't have to describe or sell 3D printing to this audience, I think. Suffice it to say that it is obviously receiving a lot of attention in material science and engineering and manufacturing. MRS Bulletin has previously published theme issues on 3D printing of biomaterials and metallic materials just in the past 2 years, and this issue continues that series. Of course, 3D printing human tissue or human organs sounds fantastic and futuristic, but as the articles in this issue of MRS Bulletin show, this is indeed what many of our colleagues are working on, and as you'll hear later in the two talks today. The goal, of course, is precision-engineered tissues, organoids, and eventually full organs using living cells, bioink, support materials, and appropriate processes. The two guest editors of this MRS Bulletin issue are Adam Feinberg of Carnegie Mellon University and Jordan Miller of Rice University. And I would really like to thank them for their hard work and effort in putting this excellent issue together. Adam and Jordan, fortunately, have also graciously agreed to be the hosts and moderators for today's webinar, and it is my pleasure now to introduce them to you. Adam Feinberg is a faculty member of Biomedical Engineering and Material Science and Engineering at Carnegie Mellon University. He directs the Regenerative Biomaterials and Therapeutics Group, which develops materials-based engineering strategies to control the 3D self-organization and assembly of various cell types into ophthalmic, cardiovascular, and other tissue types. Feinberg received his BS from Cornell University and his PhD from the University of Florida in 2004. He completed a postdoctoral fellowship at Harvard University before moving to Carnegie Mellon. Adam has received the NIH Director's 2012 New Innovator Award and a NSF Career Award in 2015. Jordan Miller is a faculty member of bioengineering at Rice University. He directs the Physiologic Systems Engineering and Advanced Materials Laboratory, which employs synthetic chemistry, open source 3D printing, fluid dynamics, and molecular imaging to understand the process of vascularization and assemble living tissues with complex organization. Jordan received his BS from MIT in 2003 and a PhD in bioengineering from Rice University. He was a postdoctoral fellow at the University of Pennsylvania before moving back to Rice as a faculty member. So Adam and Jordan, thank you for hosting and moderating this webinar today, and of course for guest editing the MRS Bulletin issue, and I will let you take it from here.
All right, great. Well, thanks, Gopal, and thanks to you and your team at MRS. We're very excited about this special issue on 3D bioprinting of organs. Thanks also to the contributors of the special issue, some of which you'll hear from today. And thanks to the audience for joining us today on this discussion. We really are excited to tell you more about our perspective on the field and learn from you what your interests are in potential future applications. So if we go to the first slide here, we wanted to put this more into context for everyone. So where is this process coming from? Why do we need to 3D bioprint tissues and organs? And this evolution has happened over the past few decades, where initially there was the thought of the bionic human, the idea that almost any problem in the body could be treated with a device. And you can see a lot of these that were science fiction back in the day, they're now reality. You can get a total knee replacement, you can get a hip replacement, you can get a pacemaker, there are cochlear implants to allow people to hear, people are working on retinal implants, and entire artificial hearts. There's a growing realization that this idea could not necessarily scale to every problem in the body. A lot of the organs in the body have key biochemical functions that we don't know how to recapitulate with a material. For example, we don't know how to make a plastic or a metal that can metabolize alcohol or aspirin like the liver can. And so there's a growing trend towards regenerative medicine to supplement and complement a lot of the innovations that have happened in the device industry. And could we build functional provisional tissues made from a patient's own cells that could recapitulate their biochemistry and restore function in the organs? So if we go to the next slide, this has already had some successes in the clinic. And regenerative medicine has been used to treat a wide variety of conditions. You can see some of the regenerated tissues and tissue scaffolds that have been fabricated and used successfully already in humans. So at the top here, we have a very thin sheet-like material that can serve as an artificial skin substitute made from processed collagen. In the lower left, we have an artificial cornea, which is the outer layer covering of the eye. And in the lower right, you see it was a 2D scaffold that was sewn into this 3D shape, and that made a functional urinary bladder. The urinary bladder is spherical, but it's mostly hollow. And so this sheet-based technology could be used to restore function in these human patients. And the question that we're left with is, how do we scale these technologies into the more complicated organ system? So if we go to the next slide, you can see some of the challenges in what are called the solid organs or the volumetric organs that are found in the body. So these are very large organs, some of them more than a liter in total volume, but they have a very complicated internal architecture. And you can see the liver is a perfect example of this. The liver is a very large organ, but almost half of it is blood vasculature. And the vasculature you can see on the right here from a CAT scan of the vasculature in a mouse liver. It has a very complicated, interconnected, multiscale architecture. And so one of the implicit ideas behind bioprinting, if we go to the next slide, how do we address this complexity? So we have the idea of structure-function relationships, and in biology, that we have the mantra of form follows function. That is, once you understand a function of a biological structure, you can then look back at the form of that biological structure and understand how that form supports the function. In regenerative medicine, I believe we're asking really the converse question, that is, will function follow form? So if we can build living tissues who have the form that matches native tissue, native organ structure, that is vasculature, that is microstructures inside the organs, that is many different types of cells in different positions in the organoids, then will that engineered structure have the same function? And what gets people very excited about this potential is the accessibility of 3D printing. And I'll turn it over now to Adam, who will tell us more about how 3D printing is being used and harnessed for this technology.
Great, thank you, Jordan. And I also just want to thank Jordan. Really was great to have you co-edit this issue, all the contributors, as well as the entire MRS team. On this first slide that you're seeing now, it really just goes over some of the typical ways that 3D printing of soft, living, and biological materials is currently done. And these really build off of many of the techniques used more broadly in the 3D printing space, with some special kind of modifications and considerations for the unique material properties of things that are soft and living. Really, the most common way would be extrusion printing, shown in the upper left, which is where a syringe is used to extrude and deposit material either onto a surface or into a support material. This is also very similar to the way many current thermoplastic printers work when they extrude a soft plastic that rapidly cools. In the upper right is the inkjet printing, very similar to an inkjet printer that you might have in your office, where you have a multi-nozzle array that deposits very small volumes of liquid that rapidly gels or dries. In the bottom left, you have selective laser sintering. This is where a laser is used to raster across the surface of a powder bed. The powder may contain small particles of, say, PCl, polycaprolactone, or other materials that are fused together by the laser beam. And then finally, you have stereolithography. You could have both a laser beam-based system similar to selective laser sintering, where you can raster the beam, or you may have projection stereolithography, where you may use something like a projector, DLP-based projector, to illuminate an entire field of view at one time. So these are some of the common ways that different kinds of 3D printing are done. If we go to the next slide, there's really a wide range of hardware currently being used to do this, both commercial systems as well as lower-cost open source-based systems. In panel A, we see the 3D bioplier by EnvisionTech. This really represents a high-end commercial solution that can go into a biosafety cabinet. It really has as high a precision as you really need for doing almost any level of fabrication, and has multiple tool heads so you can combine different types of materials deposition. In panel B and C, we see a modified MakerBot, some work out of my own lab, You can actually see this bioprinter is even made out of wood. This is one of an earlier model of a MakerBot. And what we've done is replace the thermoplastic extruder that would normally deposit ABS or PLA with a custom-built syringe extruder. And this is an example of a low-cost printer, but also an extruder design that we've actually released also via open source, and you can actually download and print this and make your own modifications. Kind of similar to this kind of open source or lower cost system, but more in terms of a commercial solution is shown the BioBots printer in panel D. Very similar technology to what would be in a MakerBot, but now in a more turnkey solution that really any researcher can go out and buy and implement rapidly in their lab without really having to know how to, build and assemble their own bioprinter. And then in panels E and F is a SLS selective laser sintering based modification out of the lab of Jordan Miller, where they've actually taken a standard laser cutter and modified it to be a SLS-based 3D printer for using PCL and other biodegradable polymers. It's really a range of options here that you can use to fabricate a vast array of materials for these applications. On the next slide, we really look at kind of a standard paradigm that one can consider when trying to print a tissue scaffold or ultimately an entire organ. And this really involves a wide range of imaging, analysis, and then fabrication techniques, but kind of keeps it under the umbrella of kind of complete digital fabrication, which is one of the exciting, I think, aspects of this technology, where you can take an organ or tissue of interest. In this case, we're showing an embryonic heart from the chick. We can now label specific ECM and cellular components with antibodies or other fluorescent markers, do 3D imaging using confocal or multiphoton, or at larger length scales, MRI or CT imaging. From that, we can segment a 3D CAD model. And then once we have that CAD model, we can feed that into a program called a slicer, which takes a 3D model, an STL file, and converts that really into machine movements for both the position and the deposition rate of the material being extruded. And once we have that, that feeds directly into the printer, where we have the ability to use multiple print heads with different bioinks and cell compositions, and then can print a tissue scaffold. And here we just show an example of this heart printed in an alginate, shown in cross-section in the green, and then also under dark field illumination. In this case, this heart is roughly about 1 inch in diameter. And this is a scaffold that is acellular, but really, I think, suggests some of the complexity of what can now be 3D printed. And, the issue of this MRS Bulletin also highlights a lot of the materials challenges we're facing in now taking this technology further for a wide range of applications. Along that line, on the next slide, I'd like to introduce our first speaker, Michael Galinsky from the University of Dresden. His talk is titled Novel Strategies for Bioprinting of Macroscopic Constructs. And following his talk will be a question and answer session led by David Killian, a co-author on this manuscript, as Dr. Galinsky was unable to join us for the live portion.
Hello, everybody. Welcome to my online presentation entitled Novel Strategies for Bioprinting of Macroscopic Constructs. My name is Michael Galinsky. I am heading the Center for Translational Bone, Joint and Soft Tissue Research at University of Technology in Dresden, Germany. And welcome to this event. Before I start, I want to mention that I will not give a broad overview about bioprinting in general. So I hope that you all are already a little bit familiar with this technology. I really will focus on the question how we could bioprint macroscopic constructs, macroscopic cell-containing scaffolds, and want to introduce some thoughts we have developed on this topic, which also have been published in this special issue of MRS Bulletin. If you are interested in what we are doing in this field of 3D printing and bioprinting, I want to refer you to the two web links on the bottom of the page, especially the right one with the German spelling of the term fabrication with K leads directly to the part of our webpage dedicated to 3D printing and bioprinting, where you can find also all the papers we have published on this field up to now. As you know, additive manufacturing is a really fast developing field of research since a couple of years now, which also already has introduced to several applications in industry. This slide, coming from a paper already more than 10 years old, shows some of the most important additive manufacturing technologies, and all of them have been translated to biomedical applications in the meanwhile, like, for example, the fabrication of patient-specific implants based on ceramics or metals with methods like selective laser sintering or melting. For bioprinting, only methods can be used which can be finally utilized at physiological or room temperature, not making use of high energy, like, for example, the laser beam needed for selective laser sintering. So I will focus on methods which are called direct printing here in this slide, and this is a term covering everything concerning extrusion or inkjet-based additive manufacturing. For all of these additive technologies, of course, the basic principle is similar. So we need to have an virtual model and computer-aided design model of the object we want to manufacture. This has to be sliced, so we have to define the layers, because all the additive manufacturing technologies are based on a layer-by-layer principle. And after the slicing process, the file is more or less given to the additive manufacturing instrument, whatever it is. And in this layer-by-layer method, then the real object is generated. Concerning bioprinting, as I've mentioned before, we can only use the methods which can be called direct printing, and this subsumes inkjet-based as well as robotic dispension, as it is called here in this scheme, taken from a paper published by Jos Mulder recently. As the inkjet-based methods are handling either cell aggregates with maybe 100, 200 microns in diameter, or hydrogel beads loaded with cells, they are not really suitable for bioprinting of real macroscopic constructs. Therefore, I want to focus on the extrusion-based technologies in my lecture, which we mostly like to call 3D plotting, but the terminology is definitely not yet well defined in the field, so you definitely will find several names for these technologies. The general problem we are facing with extrusion-based bioprinting is that if we want to make well-defined, especially macroporous scaffolds, we need rather high viscous printing materials because the material has to provide an significant strength to the structure. On the other hand, if we want to include living cells in the printing process, this is definitely not possible because mammalian cells do not accept in vitro, outside of a living organism, to be embedded in a rather stiff matrix. If you think about conventional cell culture, the cell culture medium, and this is the environment of the cells, just is water, so a very less viscous material compared to the common bioinks. And therefore, in most of the bioprinting studies you see nowadays, people work in a more or less compromised region. So the bioinks, the material, the hydrogels used for suspending the cells for the printing process are not really suitable for a good shape fidelity, and the cells are also not really happy because the hydrogels already tend to become a little bit too stiff. Therefore, we all want to move to this yellow region. So we all want to establish new strategies to combine these two properties, especially, of course, this is necessary if we really want to step forward to macroscopic cell-laden constructs. And the clinical necessity for this are, of course, finally real defects, like a huge cleft lip and cleft palate in this young boy here. So a combined weak defect of the upper jawbone and the soft tissue nearby, skin, muscle, fat tissue, oral mucosa. So to treat such a defect really in a patient-specific manner, we definitely would need macroscopic cell-laden constructs, and of course, by the way, also constructs covering different types of tissues and therefore probably consisting of different materials and of course different cell types. So this is more or less the driving force behind this type of research, not to speak about real human organs. This is a very long way to go, something we probably never will reach, but something we definitely could reach in the far future is to make artificial tissue constructs for such types of defects in humans. For the review paper published now recently in the special issue of MRS Bulletin, we tried to organize the studies we found concerning how to bioprint macroscopic constructs in different categories, and we defined four. One we want to call technical solutions, another one external stabilization, internal stabilization, and finally core shell bioprinting. And in the next couple of slides, I want to show you examples, mostly from literature, a few also from my own lab, how these different approaches successfully have been used for bioprinting of macroscopic constructs. So to start with the technical solutions, what do we mean with this? For example, to include cooling or even freezing processes during the bioprinting. It also could be used if one is start to crosslink the bioprinted construct already during the fabrication process, and therefore to crosslink layer by layer, and not only the complete scaffold after the printing process has been finished. Another option is to use a stabilizing liquid as an more or less supporting material, support concerning the negative effects of gravity. If you think about the soft hydrogels we have to use for bioprinting. And last option I want to mention is photopolymerization. Again, if it is already applied during the printing process, but of course this is limited to photo cross-linkable bioinks. So just a few examples for these approaches. One comes from the lab from Horst Fischer here in Aachen, Germany. He has published recently about utilization of an ultra-hydrophobic fluorocarbon. Try to show this with a mouse on the slide. So the printing process is done in a liquid of a completely inert organic solvent, as I've mentioned, ultra-hydrophobic fluorocarbon. And therefore, this material stabilizes anything you are extruding in this volume. And therefore, for example, geometries like this hollow tube could be fabricated with a size of around 1 centimeter. Behind this is a 1 cent coin. And this was done with a rather low concentrated agarose biopolymer hydrogel as bioink, which definitely would collapse if you would extrude this, if you would print in air, not having this stabilizing but inert liquid. Fortunately, these ultra-hydrophobic solvents are good solvents for oxygen and therefore support survival of the cells. But of course, finally, after some cross-linking process, you have to transform you have to put your construct in the normal incubator in aqueous cell culture media. Another example, looking more complicated than it finally is, makes use of this in situ cooling and freezing process. Whereas in the study shown on the slide before, everything was warmed up to physiological temperature, 37 degrees. Here, everything is done at low temperature. So the cells are mixed with an alginate hydrogel at 4 degrees Celsius. This is also the temperature of the more or less reservoir of the syringe in which the cell suspension is stored. But then the printing process is done on the building platform, which is cooled down to a temperature of -10 degrees, leading, of course, to fast freezing of this aqueous alginate-based bioink. And this, of course, significantly stabilizes the structure. Therefore, the team has been able to demonstrate that they can print with a low concentrated, only 3% alginate hydrogel, very defined three-dimensional macroporous constructs, which then in the next step are cross-linked in a calcium chloride solution, again cooled to +4 degrees Celsius for 2 minutes. And then after washing step, the cell-laden construct is put in the incubator. So this works well. Limitation, of course, is here that the heat transfer gets slower and slower the more layers you are printing on top of the cooled stage. This probably is made of metal, therefore has a good heat transfer rate. But the more layers are printed, the slower the cold is transferred to the next layer. And therefore, this is a nice option, but maybe not the way to go if you really want to have truly macroscopic, so centimeter-sized cell-laden scaffolds. With these two examples for the technical solution, I already want to go forward to the approach we want to call external stabilization, which is maybe the most common one if macroscopic bioprinted scaffolds are fabricated. What is done here is that the soft cell-laden hydrogel is combined with a much stiffer supportive material like a thermoplastic polymer. In most studies published in this field up to now, polycaprolactone is used due to the low melting point of this polymer. But more and more also other materials are successfully tested in this approach. Another possibility is or I have to mention before, the maybe negative side effect of this approach is that if you really use a very soft cell-laden hydrogel, you end up with a non-porous construct. You are printing a porous, for example, PCL-based scaffold. So the whitish strand here, the grayish strands are the PCL strands, but then all the pores, all the macropores are completely filled up with a cell-laden hydrogel. And therefore your final object is non-porous. And as we know that the cells, of course, would need oxygen and nutrients, we automatically will run into problems again if we would use this approach for real macroscopic scaffolds. Therefore, alternative is not to use a very soft bioink, but a stiffer bioink, show you example later, so that we can generate still macroporous scaffolds. Or a third option is to use a third material, a sacrificial material, which is dissolved after printing and cross-linking, so that then again we would be able to generate open macropores, which would help to provide oxygen and nutrients to the embedded cells. The first paper published in this field comes from the group of Joost Mulder in Utrecht, the Netherlands, published already in 2011, demonstrating that this combination of PCL, here the white strands, and in this case 2 different cell-laden bioinks is applicable and of course significantly helps to stabilize this type of construct. And they also show already in 2011 that they can print as big scaffolds like this very simple model of a human ear with a length of around 3 centimeters. Same direction, a newer paper coming from the Atala group, Wake Forest, United States. They made more or less the same, but added additionally a sacrificial material, pluronic in this case, which can be dissolved after the printing and stabilization process so that an overall macroporous construct can be generated. And also they have been able to print such an human ear-like construct based on this combination, again using PCl as the mechanically stable polymeric material. One example from our own lab, here we tried to generate a completely open porous structure designed for bone tissue engineering. So we have replaced the thermoplastic polymer PCl by a self-setting calcium phosphate bone cement, a material we have worked quite a lot on in the last couple of years, published already a few papers on using this for 3D printing. And yeah, you nicely can see here the cement and rather stiff cell-laden hydrogel I will speak about a little bit later, so that we still have open macropores, which of course are helpful for oxygen and nutrient supply to the cells. What does the structure look like one day after printing? As I've mentioned, the cement is a self-setting material, mostly based on the chemical reaction from alpha-G calcium phosphate towards hydroxyapatite, the calcium phosphate phase of human bone. This is the stiff, supportive part of our combined scaffold. And here the little bluish dots, these are healthy and active human mesenchymal stem cells. We used an immortalized cell line, H3 MSC, and we stain this with the MTT stain, which is only transformed by really active and healthy cells to this dark violet formazan derivative. So as a nice proof that we have living cells here inside. Looking on later time points, 2 weeks and 3 weeks after printing, these are our live dead stainings. You nicely can see that we still have mostly live cells here in our hydrogels. We still have completely open macropores between the cement strands, so the hydroxyapatite strands, and our hydrogel. And astonishingly, we observed that after 3 weeks of culture, first cells have started to migrate out of the alginate-based hydrogel onto the surface of the stiff calcium phosphate cement strands, because human mesenchymal stem cells need to adhere using the integrins to something they can bind to. They don't have, of course, integrins to bind to the algae-derived polysaccharide alginate, and therefore some of the cells seem to prefer to stick to the calcium phosphate surface, which provides a maybe more natural surface to these cells, especially, of course, if we drive them towards the osteogenic lineage. Moving towards the next class of opportunities for bioprinting of macroscopic scaffolds, we would like to call internal stabilization. And with this, we are meaning the increase of the viscosity, which of course has to be done without diminishing the cytocompatibility. So please remember the scheme I have shown in one of the first slides of my talk. It's not a solution just, for example, to increase concentration of the biopolymers. This definitely would lead to cell unfriendly conditions, so the cells would not be able to survive either the printing process or then further cultivation period. So we have to use a little bit and more sophisticated approach. One is based on addition of nano or microfibers or particles, another on blending of different materials, different polymers. Another one, of course, again, is the cross-linking, I already have mentioned before. And of course, this approach also can be combined with others, as you have seen this in the slide before. So we have used such an internally stabilized bio-ink with this external stabilization, making use of the rather stiff calcium phosphate bone cement. Again, examples in this for this application. This is work from the Gartenholm group from Göteborg, Sweden. They have combined, again, alginate as the basic biopolymer with bacterial nanocellulose microfibers in different concentration ranges using very less concentrated alginate, but partly rather high amount of this bacterial nanocellulose. And with this, they could achieve a number of different bioinks. They could demonstrate to be suitable for different cell types. And this is one of the few bioinks which already has been commercialized by this group from Sweden. So the company is Cell Inc. I definitely don't want to make advertisement for them. We have absolutely no connection. We are not using their inks, but I want to mention that there are, of course, now some bioinks which are commercially available, and these are these combinations of composites of alginate and nanofibrillated bacterial cellulose. Example from our lab, we again used alginate as the base material, again 3% as a maybe common concentration. But what you can see from this photograph here, taken from a only 4-layered scaffold, that the shape fidelity is really not very good. The pores, which should be rectangular, already after 4 layers start to become roundish. So this is an bio-ink which definitely is not suitable for macroscopic construct. So what we did was extremely simple. We just blended the alginate with another biopolymer, methylcellulose, 9 weight percent. With this, we achieved a much better hydrogel with a much more suitable viscosity. Here we nicely could print even 50-layer scaffolds with very nice and still well-shaped scaffolds. Here photographed from Z direction. Reason, and can show you the printing process with this little video film here. So this is how we do this in our lab with the GESIM printers we are using. This is now, of course, time-lapse. And as you see, we can print in air as the viscosity of the material is suitable for this. So we don't need any stabilizing liquid, and we can do this even with a, for example, 50-layer scaffold you have seen on the photograph before. The reason for this is, of course, the significantly altered viscosity of the blend in contrast to the pure alginate. So these are the values for pure alginate, shear stress, and viscosity. Please look on the scale of this graph here in comparison to the blend, alginate methylcellulose, where we have completely different values. And especially we have a very nice shear thinning behavior, which I'm sure you already have heard about, is of course one of the relevant properties materials should have if you want to use them successfully in bioprinting. Due to time limitations, I will not go into details now. The nice thing is for using methylcellulose to blend the alginate is that the methylcellulose, of course, is not cross-linked by calcium ions, in contrast to your alginate. And therefore, the methylcellulose is more or less quantitatively dissolved already in the first week of cell culture. So here we just have stained the methylcellulose with a conventional cellulose staining, chlorine zinc iodine solution leading to this dark violet color. And you can see that between day 1 and day 7 storage in cell culture medium, most of the methylcellulose just has been washed out. And therefore, the viscosity is again going down towards a region which is necessary for long-term cell survival. But the scaffold, of course, due to the cross-linking process, cross-linking of the alginate part still is stable, and so we can culture the structure over several weeks without any risk of decomposition. This works well. We tested this with primary human mesenchymal stem cells. Again, comparison between the pure alginate used by many groups worldwide and our novel blend. Upper row of images is day 1, so directly after printing. Lower row is after 3 weeks of additional cell culture. And for better visibility, we have separated the channels. So we have the live cells with green fluorescence in the live dead staining, and the dead cells showing red fluorescence. Only very few red cells in both cases, and maybe even a little bit less dead cells after 3 weeks of culture in our new blend compared to the pure alginate. So I think it's a nice material, at least as good as the pure alginate, but with a much better shape fidelity and therefore a significantly better opportunity for bioprinting of macroscopic structures. And we successfully have used this blend in the meanwhile, not only for bioprinting of primary human mesenchymal stem cells, as shown before, but also for bioprinting of pancreatic islets, primary derived from red tissue. And we have been more or less for fun the first worldwide to introduce the bioprinting to non-mammalian cells. So we published a couple of papers now on bioprinting of microalgae. As you can see it here. And just a couple of days back, we published, again, to the best of our knowledge, the first paper worldwide on 3D bioprinting of plant cells. You can find this in the journal Biofabrication. Another example coming from our group concerning composite formation. Here we have tried to replace a part of the methylcellulose by a nanoclay material called leponite, very cheap material, commercially available. This was work we done together with a group of Richard Orefo, University of Southampton, United Kingdom. And again, of course, the key property was the viscosity. So by adding distinct concentrations of leponite, we have been able to significantly enhance viscosity, increase viscosity compared again to the 3% alginate, and therefore making this composite blends much more suitable for printing and bioprinting. Also, this has been published recently in Biofabrication. Due to time limitations, I only want to show you a few photographs of scaffolds we have printed out of this composite material. So this open standing hollow tubes, again printed in air. And I want to point out especially here photograph J. This is a photograph from the side. And therefore you can see that we have open pores even from the side, which is not possible with a blend consisting only of alginate and methylcellulose. Here we had the open pores only in Z direction, but not in X and Y direction, so the viscosity is even better here. We used this blend for bioprinting with some nice data, but I don't have included this in the talk. You can find it in the recently published paper. So last few slides on the fourth group of technology we want to call core shell bioprinting. The principle behind is, again, the combination of two different materials, but not in different strands, as you have seen this before with the polycaprolactone or the calcium phosphate bone cement, but here inside of the strands, which means you are combining two different materials in a core shell fashion. One material is the shell and the other one is the core. The stiffer component can be the core, or, and maybe this is the more effective way to do it, it could be the shell material, and therefore helping, protecting, supporting your soft hydrogel, which then, of course, has to be the core material. You have to keep in mind, due to the very close interaction of the two materials, that of course there may not be any cytotoxic effects from the second material, which therefore has to be selected quite thoroughly. Also, my group is working in this field, so this schematic has been taken from a paper we published last year on core shell printing. Only a little bit bioprinting included here. So of course you need a double extrusion nozzle, which then is connected to two reservoirs, two syringes of your printing device, so that you can extrude simultaneously two materials here, shown schematically with the blue and the gray color. And if you mount this to your 3D printer, you can make scaffolds out of this. Again, a result from literature, paper published this year by the group of Yin Yang, University of Nottingham, United Kingdom. They have used a quite complicated material combination and photo cross-linkable material as shell and a soft collagen multigel blend as the bioink, loaded with a couple of different cell types they have tested successfully. And with this, they have printed 3D scaffolds, could show with a live net staining that the cells are alive. You can see here the shell material protecting and mechanically supporting the soft bioink with the living cells in the center. And they were able to print really macroscopic scaffolds here with a edge length of 2 centimeters, a cube-like structure. We have done similar work, still unpublished. Can show you the setup. So this is the double extrusion nozzle, of course, connected to two different syringes for the two materials. We also printed successfully macroscopic scaffolds, maybe even looking a little bit more defined than those printed by the colleagues from Nottingham, to kid them a little bit. We also could prove living cells. Here we have included human endothelial cells, primary endothelial cells, with a multigel-based core, and the shell material we have used was this blend consisting of alginate and methylcellulose you have seen before. So very similar work and a nice option for printing of macroscopic scaffolds. With these examples, I want to conclude my talk, summarizing that there are several strategies now available for successful 3D bioprinting of macroscopic constructs, but macroscopic in the moment means around 1 cubic centimeters. Already suitable for the treatment of real significant human tissue defects, but of course still far behind of things like a human liver. And this definitely still remains a dream concerning bioprinting. Of course, materials and technologies has to be thoroughly selected for the specific needs of the tissue you want to make. So definitely a piece of bone would need a completely different material combination than a piece of soft tissue or a piece of an artificial organ. So there is not one technology, there is not one type of bioinks, but it really has to be selected for your applications. Maybe combinations of several of the approaches I have demonstrated might lead to even better results, and I have demonstrated a couple of them. For example, the combination of external stabilization, think about the calcium phosphate bone cement, and the already internally stabilized, rather stiff bioink. The blend of alginate and methylcellulose needs maybe two especially interesting properties. What I have maybe to criticize a little bit is that many of the bioprinting studies which have been published in the last couple of years make use of cell lines, and these are mostly cancer-derived cells, which are very robust, and therefore definitely are not the best model for the primary cells. And finally, we want to make bioprinting with primary human cells, or of course with non-mammalian cells, and so we now really should step towards the level that we already include these, of course, more sensitive primary cells in our studies. Because if you develop technology and materials which only work with cell lines, this would definitely not bring us far forward. And finally, I want to mention that you, of course, all know that with the exception of articular cartilage and blood vessel segments, all tissues in the human body are vascularized. So we have to keep this in mind. We need at least macropores so that oxygen and nutrients can diffuse to the cell-laden bioink components of our constructs. And it would be even better to include really vascular-like structures. But this is an own topic I could not even mention today. With this, I want to thank my group and several co-workers, companies, funding agencies. I want to thank you very much for listening to my lecture. Again, want to point out that using this short link with a German spelling of biofabrication, you can reach our web pages and find all the papers we have published so far on this topic. And finally, I have to state that unfortunately, I will not be able to participate in the question and answer session because at the day this webinar will be held, I am at a conference in Athens in Greece, and therefore definitely not able to do that. But my co-worker and PhD student David Kilian, who is first author of our MRS Bulletin paper, he is available and of course would be happy to take your questions and answer they as good as we are able to do that. Thank you very much and goodbye.
All right, great. Thank you so much to Michael and to David for both contributing to the special issue and for taking part in this webinar. So we wanted to get to some of the questions. So the first question we have for David Kilian is, what are the strategies to ensure the viability of cells inside of volumetric constructs and therefore the survival of the whole tissue itself?
Hi Adam, hi Jordan. First of all, let me thank you and everyone at MRS Bulletin for inviting us to contribute in the issue and the webinar. So facing this first question that you just introduced, basically we should have a look basically at the reasons for dying cells inside our construct. So basically, if people observe non-viable cells right after printing, 1 or 2 hours after printing, right after a printing procedure, this is mainly due to the processing procedures. So speaking about mixing the cell suspension inside the hydrogel, the temperature shifts, the shear stress from extrusion in the printing nozzle, different cross-linking mechanisms. So basically those are approached via strategies that we just saw, so modifying the procedures, optimizing the bioinks and procedures to make the process less harsh basically for the cells. However, if we speak about cells that die due to the lack of oxygen or nutrients inside the volumetric structure after some time, it's basically about the limit of diffusion of those factors inside the volumetric structure. So there's certainly studies out there showing that in the middle or the central area of the strand, there's sometimes a lower number of viable cells compared to the peripheral structures. So the strategies to kind of tackle this are, first of all, the macropores that you saw in most of the introduced studies and the introduced constructs of several hundreds of micrometers, basically to ensure the access to oxygen and cell culture medium. However, therefore, high viscosity of the material is required, so to really keep those pores and the macroporous structure even in horizontal range. Some other studies also try to include, so to say, small vessels, basically via sacrificial materials, for example, to fill the surrounding space with some additional hydrogel that doesn't dissolve, and then dissolve sacrificial material, then kind of lining up the walls even with endothelial cells, so kind of create small vessels inside there. However, if you think about the capillary systems of the liver or kidney or more complex organs, this is quite hard to mimic, and still you would need some connection to artificial system. But that would be basically the strategies to tackle this.
Great, thanks so much, David. So I guess a related question would be, so this is about viability during printing, and then you hinted at having some vessels in the printed constructs. So to what extent can you culture these constructs through time? Can we keep these cells alive over days, weeks, months? What is the expected stability and after their actual printing?
Okay, so basically, speaking about the in vitro studies, or most of the studies that we just introduced, they are shown for cultivation over several weeks. So both for like mechanical conditions or mechanical properties, also swelling ratio of the material, strand diameter, so really stability of the material itself, of the 3D construct, but also on the biological side. So basically, people show it for several weeks, and it's also, for example, speaking about the differentiation of stem cells, for example, in osteogenic or chondrogenic lineage. So because we usually work with bone or cartilage tissue or cells, this takes 3 weeks basically. So that's the time frames that are shown in the studies. However, moving on for potential in vivo application. I mean, if you are basically planning to replace lost tissue or organs, you want this to be a permanent solution. So speaking about maybe the preliminary animal models or something, those structures are shown like after several months then about their stability and what's going on in there. Also, another important aspect is basically the degradation of the material, really the behaving inside the body, inside a physiological system. Of course, this really depends on the material that you use. However, what is very important in this context is that in a physiological state inside the body, you're always we always speak about a constant remodeling of tissue and organs also from a biological aspect. So cells are replaced, the surrounding matrix is basically remodeled, degraded over time. So basically, you just give a temporary construct, bring in cells, bring in structure, or the potential factors really to stimulate regeneration in that case.
Well, thank you, David. The next question really focuses a little bit more on some of the material properties of what you're printing. So, when you look at the alginate compared to the alginate with methylcellulose to improve print fidelity, those materials had different rheological properties. Can you comment on the importance or need for specific kinds of viscosity or shear thinning behavior or yield stress or thixotropy?
Yeah, sure. So basically, as introduced in the talk, this shear thinning behavior is like one of the most critical and most important factors or aspects for extrusion-based bioprinting, since this basically means when increasing the shear stress or shear rate on some material that the viscosity basically decreases. So when bringing together those materials, you end up with some non-Newtonian behavior basically. So viscosity decreases as the shear rate increases, basically due to the reorganization of the polymer chains in there. So they are more stretched in terms of this and less entangled maybe. So when thinking about the actual nozzle that we extrude the material through, they're kind of less viscous and are extrudable in that case.
Great, thank you. Kind of also related to the materials being printed, you did a lot of work with algae and methylcellulose. So some of the questions are along the lines of other materials that you have or can be printed in these systems. And one question specifically was about matrigel.
Yeah, very interesting question as well, how to kind of apply this quite cell-attractive gel that has been used for a while. However, when speaking about bioprinting and extrusion-based plotting, also for this material, I think you would have to add another polymer or some material to get the shear thinning behavior or to end up with some extrudable paste. So we don't work with this actually too frequently. There was some of the studies on the core shell printing introduced. So basically for the core material, I think it was used in some of the, it's been used in some of the applications. So really, this means that we have an additional, more stable or more higher viscous material surrounding the actual matrigel of the cells inside.
Great. We had another specific question I'm not sure we can go back to slide number 13, but there was a question about how the porosity was achieved in the calcium phosphate material, which was used as the external stabilizer, because the cells were able to enter inside that region after 3 weeks. And so the question is, how do the cells seated on the alginate surface, how were they able to enter inside that structure?
Okay, so reading this question, actually, there are some aspects to note maybe. So one thing was that probably, there's some microporosity definitely in the calcium phosphate material. However, what is important to note is that probably the cells were rather on the surface of the calcium phosphate phase that we found them. And plus, they were not actually seated on the alginate, so they were really printed inside the alginate methylcellulose structure, but still kind of migrated out due to preference maybe for the calcium phosphate and for the stiffer material, I would say. But very interesting question, yeah.
I see. Great, thanks. So along the similar lines of some of the multi-material work that you've been showing, so I guess the potential is to put cells embedded in some material that's soft and a larger material that's more stiff. And so can you talk a little bit more about the approaches you've seen that allow you to print macroscopic soft tissues in a bioink with a physiologically relevant stiffness?
So the question is how we basically print cells and viable cells in a physiological range inside highly viscous materials? No, sorry.
Yeah, I believe the question is about the could you do multi-stiffness printing, where some regions would be stiffer than others, and you would then have generally hard tissue, but that has soft regions with cells? I think you...
okay, so yeah.
A little bit,
so,
yeah.
Yeah, I think I got it. So, so there's approaches where basically the higher stiffness material is mainly there or largely there to support the structural integrity of the construct. So in others, there would be probably also approaches with different stiffness of materials, having cells in both gels, but this mainly depends on the cells itself as well and the cell type of cells. But usually most of them would prefer the softer hydrogels having the lower total polymer content. I'm not sure whether I fully covered the question, whether I completely understood.
Yeah, I think that addresses the question. I think, my understanding as well is that you have to really think about the needs of the tissue, and then once you design the architecture, maybe there are regions that need to be stiffer than cells would typically survive. So you need to then build that into your structure. Great. So I guess we had another question about how do you keep everything sterile during and after the printing process? And another related question, how do you prevent bubble formation when you mix alginate and methylcellulose?
So addressing the first question, basically, since it's a very critical aspect, actually, the whole sterilization procedure, since this is definitely a big difference to some other printing approaches, definitely, that you have to keep everything sterile and really also sterilize the pastes and think about which sterilization method would affect your material in the lowest to the lowest extent, probably. So basically we keep all our materials sterile, our gels sterile, and the printing basically happens below the cell culture bench, so everything in a laminar flow hood. And after that, we incubate everything in a normal cell culture incubator. So I guess this should address the question. The second part was about part of the question. Sorry, yes.
Yeah, when you're mixing different biopolymers such as alginate and methylcellulose, bubbles can form pretty easily, and that's also a big problem with microfluidics. So have you been able to avoid bubble formation when mixing? Are there any tricks you could advise people on?
It's quite, this is a rather practical question. It's definitely a big issue also, how to do the mixing of the materials, how to mix the cells in also. As soon as you or up to the point basically where you add the cells, you could still centrifuge the gel, for example, obviously. However, afterwards that wouldn't be possible. So you have to really try to do this in a very rather defined manner or smooth manner. Otherwise you would end up with the bubbles. And however, still with our extrusion-based system, it works quite fine, and we don't see any smaller, bigger bubbles or like clogging the nozzle too often, or like ending up without any extrusion. So it kind of works.
Great, thanks, David. Yeah, we had another very specific question actually about a specific tissue type. The question is about one of the biggest challenges in medicine involving diabetes, which involves the pancreas, which is a much smaller organ than the liver. Maybe that could make it more accessible. Are you familiar with where the field is with respect to helping diabetic patients?
Yeah, kind of. So basically there is also stuff going on inside the 3D printing. I mean, there's also, you have this capsule, I think, basically with beta cells even in alginate, so without any printed state, kind of to supply the insulin, for example, even inside the body. However, also there's stuff going on in the 3D printing and bioprinting field, definitely to print islet cells, so basically the pancreatic cells or cell aggregates responsible to after glucose stimulation, basically to secrete the insulin. So interesting approach and interesting work, and I hope also here we can see some success in future times.
Sounds good. So I think maybe end the question session. We'll maybe go to a more kind of a general kind of question from the audience, really around, I think, what a lot of people are feeling is that, the 3D bioprinting space is kind of an exciting area with a lot of advances coming, but also a lot of impact that I think material scientists can make. Do you have any advice, David, for students or even researchers that are looking to get into this field?
Yeah, I guess so. I mean, since I'm a PhD student, I should also know about my motivation, I guess, or about my my way of kind of entering the field. So I guess it's always about curiosity and really being excited about the topics and about your work. It's a very interdisciplinary area, so this is definitely important to note. So it brings together so many fields and so many, also people from different backgrounds. Like in our lab, we have biologists, biochemists, chemistry people, pharmacists, several engineers, bioprocess engineers, material scientists, everything. So, it's quite a broad field, definitely, to enter. But the most important thing is always motivation and curiosity about science.
Yeah, I mean, I'll also add that, I think one of the unique things about bioprinting, I know Jordan shares his thought, is that a lot of these technologies, because they're open source based, are really accessible at pretty low cost. These are things that, people can even put together in their homes or do at schools. And I think that's one of the exciting elements, because people can get their hands on these printers and then really start to innovate in the materials space. Jordan, do you have any other thoughts?
Yeah, I think it's such an exciting time to get involved. I think students that are interested, I guess the questioner didn't mention what level of schooling she was at, but I think even high school students can start to get involved, finding a local laboratory near you doing bioprinting. If you can't get into a lab, you can also go to a local makerspace or hackerspace where people are building 3D printers and just learning about how to do 3D plastic printing with consumer-level equipment is directly translatable into 3D printing of cells and tissue. And so I think having those types of experiences, no matter what level you're at, can really help you figure out if this is the right field for you, and then help you start to make real progress along with the rest of the field.